constantly beating me out trying to find new logs. And there's a couple of SDNs projects for simulating all those things. You know, like that works. Yeah. You get one of those up and running, you get it connected to you, and it starts doing the test. Oh, it does? The cool thing is you can like unlock the doors. You can do all kinds of stuff. Hard. Does it have the remote stuff? You got the kill switch, you got the they what you're supposed to do is you can call them. And the way you'd actually activate the system is you can touch the tailgate like the latch and then that would so the person is call someone and say you touch the tailgate and then they can see the sound.
No, everyone thinks that. It's a load. It's exactly. Yeah. Yeah, they always ask me, where's your Harley at? Still sitting at the dealership.
Yeah.
Oh, right. Right. Yeah, I've never been a big motorcycle person. Younger, it was like dirt bikes, stuff like that, but I never street bikes. I always joked and said I wanted to keep as much steel between me and my next victim. What's that now? Oh, I know it's fun. You know, I've been on a bike on the street. You know. Yeah, but it's like like dirt bikes. It's like either you're at stop or you're full throttle.
Definitely, because there's running strings on it. Yeah. You would see like the paths to all the files, like definitely see all of these. Yeah. You see like whatever you're making your last. See user PRR. Yeah.
Test 1, 2, 3.
Yeah, we got like two next class. And then like Google the guy's name still works there. Yeah, I still find that stuff too. Like a whole list of developers who built right into it. And you can look them up on LinkedIn and they're like, we got another guy working for it. Yeah, like trying to do like OSN on like firmware and figure out like what's he up to now? That actually be a decent job. Figure out like how all the firmware engineers work here. Yeah, seeing how many names come out. I'm getting like predictive about like this guy really sucks and he's always referring like you're like his signature is like on all these names. Makes the same mistakes everywhere he goes. That actually be a good visualization on the ground. Yeah. To just take the entity correlation map and I think the bubbles John Smith has touched this way. Because it's the same amount of time, like control the right, like I for you to like the CPU architecture contract out. It ends up being the same crap everywhere. I bet you've seen a lot of all the demo firmware. Oh, without a doubt.
What's that?
And it's literally.
Is it new now? Okay.
I guess we can get started then. So I want to thank everyone for showing up today. Today's presentation, End-to-End Security Examining Inter-Chip Communication. So a little bit about me if you don't know me. My name is Daryl Hyland. I'm the research lead for IoT technology at Rapid7. And when I use the term IoT, it's just not consumer stuff. We're talking about everything from industrial to enterprise to consumer to transportation to medical. So it kind of covers all of those different areas. So I've been in IT for 25 plus years, and last 15 years specifically in security. I came over to Rapid7's pen test team about 6 years ago as a pen tester, a principal consultant on the team. And then along the road, they offered me the opportunity to come over into research, focusing on IoT technology. And that was a lot of fun. The funny part is when they offered me the position, I didn't even know what the hell IoT was. So I'm like, hell yeah, I'll take it. What am I supposed to do? So that was kind of fun journey over the last number of years. I've been to all 9 DerbyCons. Anyone else here? All 9 DerbyCons? Oh, outstanding. And I've had the privilege of speaking this is my 7th time speaking here at DerbyCon, and it's been a blast. Sad that it's the last year, but hopefully we're going out with a bang. So, in this particular research project, as I showed on slide 1, lower left-hand corner, part 1. This is an ongoing research project. In this project, or in what we're going to talk about today, I'm not going to talk about any specific vulnerabilities. There's no published vulnerabilities right now. So we're going to talk about process, some of the things I've done, what the end game is, what we expect to accomplish in the long haul, and how we're going to move forward in the future. So I expect this thing is going to follow 3 parts, which we'll kind of use in the closeout, where we're going to take it next and where we go after that. Probably more than 3 parts, but we're going to start with the first 3 parts. So why? What's the purpose of doing this type of research? From an end-to-end security understanding, I really want to know how the functionality works. So we want to gather information about how the devices are working and functioning. We want to understand end-to-end security, because often we're challenged with, if I'm looking at an IoT technology and I know the cloud side of it is secure, they're encrypting it properly, and let's say they're communicating over Bluetooth, Zigbee, Z-Wave, and they're doing it right, and that's secure, how do I know what the end-to-end security looks like? Well, we dive into interchip communication. We start looking at what's taking place at that point, because all that encryption is typically stripped away, and now we can see the raw data transactions that are actually going through the system, and really get an understanding of the ecosystems. So why? I want to identify new attack vectors. What we can find out by looking at interchip communication around end-to-end security, and can I discern information that I can pull out and take it externally and carry attacks against the device. Vulnerability identification. Obviously, we want to find vulnerabilities so we can make products better and more secure. And then weaponizing the product, which I'll talk about a little more during this presentation. It's the idea of, if I'm looking at bridging technology for unroutable protocols, which is the focus, can I take that bridge device and do stuff to it that I can turn it into a weapon where I can use to attack other end devices? So it's one of the things we're working on. So the target focus, IoT technology, obviously, but we're focusing on non-routable protocols. An example, you have Bluetooth Low Energy, which is very common in IoT technology. For it to be internet aware, you have to have some kind of bridging device. This is where we're looking at the interchip communication to gather that detail where all the encryption is stripped away, and we're looking at the raw communications that's going to the end device to control it. So when we're looking at this is kind of the 3 typical models that I see the bridging technology laid out for chip functionality. We have, like in the particular presentation, we're focused on Bluetooth as part 1 phase. And we have the main CPU, and then we have a Wi-Fi MCU, or a main Wi-Fi MCU, as in this one right here. So this is a typical 3 I've seen so far. Now I may come across other designs for circuit designs that will break this down and maybe add other models to it. But this is typically what I've seen so far, and I've looked at 3 devices. I have 3 more in the project that I'm going to look at, so we can get a good understanding across multiple products of what we're going to typically see. So getting started. So the first part is, okay, we need to open up the device. We need to identify where we can get access to that communication. So the ways I typically do it is visual. You know, I can easily look at a device and trace runs. I can use a multimeter to trace runs. One of the other cool things is Damien did a presentation at Hack in Paris where he talked about similar stuff, where he did photo overlays. So he took a photo of the front side, a photo of the bottom side, laid them over top of each other, lined it all up, and was able to track runs and vias through the board. Really handy. He did a good discussion around doing that. So it's something to think about. And then X-rays. If you're dealing with multi-layer boards, X-rays may be a point that you can do to get a good understanding of how the circuits are laid out on the board. So the first example device that we're talking about today happened to be a Hickory smart lock. And right here we have the bridge device that's actually used to control this lock. So, and it happened to be this particular kind of layout. It had a BLE MCU, it had a main MCU, and then had the Ethernet circuitry coming in that fed the main MCU. So it gives us one main key point to inter-chip communication is mainly this one. So if you're looking at this one, it's a little more difficult because it comes in on 2 channels as Ethernet. And they usually run in each channel at 50 megahertz, so you got to put the data back together. So there's a level of complexity there that you need to consider in cases like this. But typically, we can look at the communication between these two. And when you're dealing with Bluetooth low energy devices, the communication to them is going to be UART, thus making this way much more simple as our first model to start looking at. And you're able to tap into that and actually capture all of the UART communication between the chips, and then start doing various analysis. So here happens to be the board. This particular case, here's the main MCU, here's the Ethernet circuitry, and here's the Bluetooth module. So the first thing is, you get data sheets, you identify how this is all pinned out. We try to figure out the runs, where it goes over to here, and it does tap into some GPIOs that have been configured for Bluetooth low energy as part of that communication. So, and here's actually me tapping into it. So we have, this is connections up for the Bluetooth UART transmit and receive, and the connections over here. And the reason why I have 2 connections over here is the connections between these two do not have any kind of coupling between them. They're straight connected over. And the thing I found out so far on straight connected ones, if you tap into this, if I wanted to inject data back in, it would not accept it, even on UART. But by cutting the runs, where the green marks are, we were able to cut the runs and reroute all the communication through a separate device where we can tap in with FTDIs or logic analyzers and things like that easily. And it also gave us the ability, and you'll see the breakout here. Let me see if we can get to it. So I built this small kind of breakout, and it gave me the ability to tap in on the Bluetooth side and this side over here, and the ability to open and close the circuits with a quick little switch if I wanted to inject data into the data stream. And here happens to be the rig with everything tapped in, and I got a couple Shikras hooked up to communicate with. Eventually end up with 4 different Shikras because I tapped into various other UART communication on the board to gather other pieces of data, which will show some of that information gathered from that, and obviously a logic analyzer. I always like a logic analyzer as the first thing, tapping into the circuits. Gives me the ability to quickly identify, hey, is it really UART? What is the baud rate? Validate all that information. So when I start setting up all of the serial devices to communicate and capture the data, it becomes much easier versus trying to do it the other way. So it's typically how I hook everything up. So let's look at some of the data we captured and look at some of the concepts or thought process as I kind of work through this. So here's the first communications that we captured and the command structure that came through up here. And this is after we've kind of decoded and broke it all down. Now this opened up some interesting things because I'm dealing with a Bluetooth low energy device. I assumed the communication coming through this device would be Bluetooth low energy. When I controlled the device locally with my mobile application, it was Bluetooth. But when I started looking at this data, I couldn't find a MAC address to identify the end Bluetooth device, which you often will see in some form. What I did see was this block of data right here, which turned out to be ANT protocol. Has anyone ever dealt with ANT protocol? The same thing I had. It was like, WTF, what the hell's ANT? So I went out, and this is a proprietary protocol, but there's a lot of good information out there on it. Now, I wasn't going to go in and spend all my time trying to figure out the ANT protocol. I was more concerned with inter-chip communication, but I did find out a couple major things. It allows multiple pairing, as an example. unlike Bluetooth Low Energy, where only one device can pair, multiple devices can pair to an ANT. The other interesting thing is ANT protocol is inherently used in devices like heart monitors and fitness tracker devices and things like that, sporting equipment, tile IoT. And I'm thinking, again, what WTF? Why the hell is this on a smart lock for a house? But the actual Bluetooth Low Energy device they were using was an NRF Nordic chip, and they have the both capability of Bluetooth Low Energy and ANT built into all of them. I'd never seen ANT actually used. It has the ability to pair multiple ways, which is kind of very unique, unlike Bluetooth Low Energy. I think I list 5, but it turns out to be 6. So we have everything from inclusion, exclusion settings, white blacklist. The difference between white blacklist and inclusion is some encryption capability functions associated with that. Proximity search within range, identify devices within this range, power levels you'll connect, outside this won't connect. A wildcard, connect anything for the most part. That goes both ways, whether it's a transmitter or receiver. One could be wildcard, one not. It won't connect unless both of them are wildcard or the one has the connection data in it for that particular device. This weird master-slave pairing, which is very similar to standard BLE, and the other one was a broadcast. There was a broadcast traffic. So it broadcasts all of its information, and it purely broadcasts, don't typically receive, and you can capture the data and receive it all that way. So that's all we're going to cover on ANT. Coming back over here, now that we had ANT protocol, I started looking at this whole thing. ANT does not use a typical MAC address. It uses an address structure like this. So instantly, I was able to discover, hey, we're communicating with ANT protocol. It gives me a little more information about this decode. We also come down and we have things like the command structure. 2, close the lock. 0, 1, open the lock. Fairly straightforward. We come after that and we have the key. Haven't identified how this key is derived. It's probably done off the cloud. And based on some information we're actually going to look at here. I guess I'm running a little fast, ain't I? Need to slow down. And then the checksum, which happened to be 2's complement, 8-bit 2 complement checksum for validating this data. And we went through and we tried fuzzing things in this data. And it was interesting because this timing sequence, you would think if I change the timing sequence on this and update the CRC, it would work. It did not. Any alterations to everything outside of this, obviously you change the device identifier for ANT, it's not going to work. So I was never able to get this to actually work by making any kind of modifications to some of the timing structure. So it opens up some more things. We're going to circle back on this product and take another look because I've learned more as I would onto some other devices. So it gives us a chance to circle back. But we quickly are able to identify, you know, this entire structure and all the pieces, do some just quick basic analysis, which tells us a lot. Now that we have the key, you know, we can work on how's that key derived. Can that key be replayed? What's the impact of that type of stuff? So I also was able to connect to the Wi-Fi side on this device, or the Ethernet side, and it was not encrypted. It was using MQTT. But the data within the MQTT packets was encrypted. So we had this blob of data coming through that was basically encrypted or encoded in some fashion. The nice thing is the main processor on this device had a UART console capability on it. And if anyone knows about the hardware, tapping into those is very useful for information. All the packets coming over MQTT were actually decoded and dumped to the screen, giving us more blocks of data. So in this case, we had the key that we quickly identified here. It's tagged as a key, makes it real simple. Does this equate to the key we showed on the other side? And there we go. So it was base 64, so we just run a command, echo that base 64, decode it, hex dump it, and we compare it to the key, and it is a direct match. So we know there's no alterations to the key. So the key's coming from the cloud, so we have that information, so there's no breakdown in the end-to-end security at that point. We end up with a node structure. It's coming from the cloud, it's ending up on the device, going through the bridge. We get to identify all the core pieces of the communication. We've identified that this is the key structure. gives us a chance to go back and say, hey, you know, how's this key derived? Can we identify further stuff out of other methods on the cloud to see how it works? So this is kind of quick cover on that, but a quick observation of this. It uses ANT pairing, which is kind of interesting because we have a higher level of security because it was using the inclusive exclusive functionality. Means if the device is not configured directly for that ANT device, can't communicate to it. Now the next example I'm going to be talking about, we had a device that's also similar encoded into a specific device, and we found a way to encode it to go to multiple devices, which it wasn't supposed to. So again, we're going to circle back around on this one here and see, and what we'll do is we'll capture, in that case, with this moving forward, we will capture the complete setup, inter-chip communication. How is a end-device lock actually paired up to the device, which is controlled from the cloud? Now that we can decode all the traffic and capture it between the chips, we'll be able to gather that data and possibly modify it to reprogram the device to be able to see other ANT devices, giving us the ability to do further testing or further fuzzing or injection attacks. And again, the purpose of that, as we think about it, is can these devices be weaponized? And the cool thing about this, which was interesting finding when we're talking about end-to-end security, is the fact that that key never, ever expires. If I replay that exact packet 4 months later on the inter-chip communication, I control the lock, which is an interesting concept on end-to-end security. I would want to see typical keys change or expire in some fashion. Because based on this, now anywhere in that food chain from the cloud all the way through the device, if anyone finds a method of capturing that key, it's always going to be valid and always have the ability to control that lock. So example number 2. Hoping my watch is just running slow on me. Talking too damn fast. Any questions? Okay, cool. Hack all things and drink all the booze. Yes, sir. No, the timestamp had no bearing on it. So the timestamp, well, if we come back here, the actual timestamp, which is the blue up here, like I said, I altered it. I was thinking the timestamp may have played a role in salting the keys generation somehow. That was my train of thought. Since if I alter it, the key doesn't work. And you would think a timestamp should have little or no bearing. Because most testing I've done, it rarely does when the key comes through. So we're thinking that may be some part of salt or part of the process of how that key's generated. And that's not coming from the local device. It apparently is coming from the cloud. So it's something else to consider. So great question on that there. Like I said, the key changes every time a packet comes through. So if I open the lock, close the lock, open the lock, close the lock, every time that'll be a different key because it's also a different timestamp on every one of them. But once a key is generated, it can easily be replayed. But remember, we're replaying it in the circuit, so we already control the device. The thing is, can that key have some impact external? If you can capture those two pieces of data, since the key never appears to expire, it becomes a potential risk. So, someone had a question back here? Yes, sir. This one here, because it's backwards. Each one's backwards. So you switch the bit order, and it's, sorry about that. Yeah, it is the same. So you got C2, 2C. This is 2C, C2. So it's switching the bit order for each one of those 4-byte groups. But it is the same. Okay, so let's move on to the next example. The next example, I'm not going to mention the vendor's name. Like I said, we're not releasing any vulnerabilities. This is not meant to disparage any of the vendors. This is just some research around concepts and how we can better understand end-to-end security and make products better and create methods and methodologies and potentially tools to help us do all this more efficiently. So in this one, I did a lock also. So I wanted both locks on this. So this was all generated in the last 5 days or 4 days. So this stuff was updated all the way up until like 2 days ago. Because we started finding some really interesting things as we started digging. So this was kind of fascinating as we kind of worked through this. In this particular case, it was Wi-Fi out here. So we just had a Wi-Fi MCU and a BLE MCU. And this one I did some various funky things. So here's the device. And we can see here on the Wi-Fi module, which is an Expressive, which I've found to not really like. It has its own problems. And then also the Bluetooth low energy device. So on the Bluetooth low energy device, we had coupling resistors in here, 2 of them on the transmit and receive. And I found out with these couplings, I could actually inject into the data stream without cutting the runs, which kind of opened my mind. I'm not an electrical engineer by any means. So it started me thinking on, how can we build tools in the future to be efficient across the board and possibly avoid cutting the runs in any case. But in this case here, I was wanting to tap into this device, and I needed to tap in appropriately because I found out that if I ended up loading on this side of the resistor on the receive transmit or transmit, if I loaded on the receive side of this from the transmit, that it would cause all communication to not function or fail. So then I started thinking, okay, I want to tap into this. So a lot of it's like figuring out how to tap into these devices, do it right, get data off of them. This one here had no runs on this side of the board. They all went to the other side of the board. And I was trying to find an effective way to tap into this thing. So we jumped the other side of the board and we have the runs over here. So we can easily cut the runs and tap in there if we wanted to route it through a control board. But I wanted to do, that resistor was in a place that was uncomfortable for me. So what I did on this side of the board was I cut the run like I would normally do. And then I soldered it up. And then I transferred the load resistor to that side of the board. So I reconfigured the board layout so I could better easily tap into it without making weird alterations to the other side, which worked pretty good to a certain point. Because of the way I had it hooked up, apparently caused some kind of load issues. I'm just guessing on the Expressive, and I freaking killed it. After like 3 hours of pumping data through it and power cycling it, it ended up killing the Expressive. The amazing thing is I've done a couple engagements dealing with Expressive devices on boards, and every freaking one of them I've managed to kill the Expressive module. So in this case, to get the board back up versus a whole lock set, because you can't buy the bridge separately, I actually went out and bought a whole freaking box of Expressive modules because I already pulled the firmware off the device, so I'll burn it onto the new module and put it on the device to keep it running. Theoretically, let's see how that works. So here's how I hooked everything up. In creating these little work modules like this, I actually color coded this one to make it a little easier for me. So I'm constantly trying to better the way we're going to do this. And I'll talk a little bit about what our vision is down the road and how we're going to build some tool sets around this and make this modular and functional so that we can better improve the whole testing process. So let's look at the communication on this device. So here is the lock being opened and closed. So this is before we really know what the data is. Here is the data hitting the BLE. Pretty straightforward, simple block. It's nice because in these particular devices it's not overly chatty. I've looked at some devices that it's like looking at a Microsoft box. It just won't shut the hell up. And trying to get data out of those adds a whole new complexity to it. It's like, okay, what really matters and what's just bullshit time sinks and all kinds of other crazy stuff. That's why I didn't put that device in here, because it would be screen after screen after screen of like eye charts. But this is a good example. So we send the data over, okay? First thing I look for, is there a MAC address here to identify the data or the device? The answer is no, I don't obviously see the MAC address. Here's the response back. It contains the MAC address. Get 2 responses back. When the signal hits here, it sends back that it received the command, and then it responds back with the current device status to say, yeah, the dice did open, or no, it's in a fail state or error state or something like that. So when we start tearing into this, we're able to identify some interesting things. It turned out that the first 8 bytes here passed the command structure, because in this case it was 01 and 00, or were the 2 commands for open and close in this particular device. We found out that this turns out to be the MAC address, and it's encoded. And the CRC, and I'm not an expert on all the freaking different ways of CRC, so I'm trying to figure this CRC out. And it turned out is if I just add all the bytes up to here and then add 1 to it and take the lower 2 digits, that's the CRC. So it was a little weirder than I'd ever seen. Probably one of the more simple ones. Easy math, adding. But again, that's how the UART communication flows that we're looking at when we're looking at this data. So how did we figure out the MAC address? And we did this by fuzzing. What we ended up doing was we started by incrementing every one of these. So I incremented every one of these up by 1 byte all the way across. And then change the CRC to be correct. It turns out that if I incremented any of these first 8 up by 1, I got no responses back. If I incremented the other bytes up by 1, I got a response back, but it was just an error code, so nothing really happened. And I never changed the MAC address. I'm like, oh, what the hell? So I started incrementing up by 2. When I incremented up by 2, I was able to start changing these MAC address on the device. So now we've managed to decode down where we can identify the MAC address, and here is a sample of changing those to give you an idea. We just changed the first byte, second byte, third, fourth, fifth, incremented up by 2, and we can see the various pattern. Pattern's a little more difficult there. If we just change the first one, the pattern is visually obvious. And what I did was okay, I'm busy. Let's utilize my coworkers at. We haven't got the decode complete, but I threw it out there because it was only a few days ago and said, hey guys, who likes puzzles? I suck at puzzles. I'm good at visual identifying patterns and building off that. And I assumed this is all some standard programmatic algorithm that's used to turn this 6 bytes into 8 bytes, and probably not overly complex. But looking at the pattern, it seemed a little complex. Because if you change the first 4 bytes of this, it would only change the first digit of the MAC address down the road. The second 4 bytes would change the second digit down the road. But I got an email today from one of the guys. He goes, I got the pattern, and he kind of wrote it all up on what he saw. There was a couple glitches in that we need to go back and resolve, but hopefully within the next week or 2, we'll have the entire pattern, which will give us the ability to change the MAC address going through the device, which is one of the key things we want to do. So then, since I had 2 of these devices, I said, well, let's go ahead and test how we can actually send data through from both these devices. So I took data captured from interchip on one bridge, tried to play it on the other bridge. It gave me an error code back. It was like an 81 or 85 kind of error code on that 4.1 return. So I got an error code, so it didn't recognize it. So I'm like, okay, why? So what I did was I blew everything down and I captured all interchip communication through the configuration of enabling the bridge and assigning a lock to it. And this is what we got here. So we did a remove bridge from the lock, add bridge to the lock. We captured all the data. So no matter what lock you do, what bridge you add, it's pretty much all the same. It's a standard code string, which is interesting. So then we can actually tell the device to ignore the lock. But it turns out it didn't really ignore the lock. What I ended up figuring out, and if you look at these ones, these are all the same. The only one different is this part right here, which is the standard key that's used to turn the lock on and off. Oh, one other thing I forgot to mention. The key never changes. So if you have a lock, that key coming through there is always the same key. Interesting observation. So what I did was I said, okay, let's go ahead and we'll send all these commands on inter-chip communication, follow with all these commands, and then give it a different MAC address for the other device, the other lock. And when I did that, I had the ability to control 2 locks from this device, even though it was designed to only pair with 1 lock. So now the whole idea of potentially weaponizing a device becomes available right here. Because once I identify the MAC address in the coding and hopefully the encryption or the keying mechanism, which is inherently getting shorter here, we're only up to 8 bytes, it could potentially give us the ability to potentially brute force or attack a device. We can identify somebody else's device and potentially attack it. I think I have a slate. Oh, so real quick on observations. So it does BLE pairing, which is nice. Less of a headache, no ant. Okay, BLE pairing is fairly straightforward. It has encoded communications, which we're in the process of hashing out. So I say within a week, we'll know the encoding for the MAC address, and now we'll have control of that part of the communication. It uses the same key. So every key comes through to turn that lock on, or open, or close that lock. It's the same key, never changes. And you can replay it, so it doesn't seem to time out either. At least within a week time frame. Now I'll come back 6 months down the road and try it again and see, well, how long does it run? So when it starts doing that, I start thinking, are we looking at true, we're looking at a key, but what does that key consisted of? What level of complexity goes into generating that key? And as the key space gets smaller, and the fact that they never expire, starts telling me a lot of things about the whole keying mechanisms, that it may not be as advanced as we think. Still a lot to figure out, and we're still working down that road. Okay, so what was I wanting to cover? Okay. So one other thing I didn't get in this slide, it was the last thing I did before I walked out of the building, out of my house to head here. After I was able to control the 2 locks, I start looking at this key right here. And I start altering these to see if I can still control the lock, open it and close it. Can we shorten the key space? Turned out that on this byte right here, I can increment that up or down so many bytes and the lock still controls. That's not part of the key. Something else, not sure what it is yet, but it's not part of the key. That means the key space now apparently has dropped down to 6 bytes. Smaller and smaller we get. At that level there, can we do fuzzing attacks to brute force some kind of key? Well, it really comes down to how far more we can narrow that key. One of the other things we want to do is, since these keys never change, and I don't have like 300 of these locks to get a sample of all the different keys for the different locks, I only have 2. It'll be a little harder unless somebody wants to buy me like 100 of these devices. And I figure you're not going to do that. So again, observations. Any questions on that? Yes, sir. So I haven't put a lot of time into reverse engineered firmware. The idea is, it may sound strange. One, I'm not the greatest reverser, so it takes me like 5 times longer than any normal person that does reversing. But I didn't want to confuse. I wanted all the data to start off with making as much analysis as I can based on data that I can pull from the circuit board directly in communications. Because that's what the whole thing's about. Because there's a number of times you're not going to easily get the firmware off these devices, without some kind of, power glitching attacks or things like that. So that adds more level of complexity. Both of these devices were nice enough that they never bothered to set the no readback bit, so I was able to get the firmware. So I have the firmware. So I've taken some really basic level checks in there and say, okay, am I identifying anything that looks like a key structure that could be used for decoding? But I haven't put it up into any kind of debug or anything like that to wholly identify that. That'll probably be one of the things down the road. Once you get to a certain point and go, okay, I'm stumped, I can't pull any more out of my ass, let's go ahead and look at a little deeper look at the firmware and see if that reveals any more answers to the keying mechanism or the decoding of the keying mechanisms. So good question. Any other questions? Okay, testing processes. Kind of the, why am I doing this again? What am I looking for? So I want to look at replay attacks. Can I do replay attacks within this? Can I map the communication? I want to map the communication across the board because some devices you may have multiple communication paths to various control devices. The control mechanism is still coming down the same, as in, it's still coming from the same cloud to control some devices hooked to it, but you have some more advanced bridges that may have Bluetooth Low Energy, Zigbee, Z-Wave. So start thinking about that. How do we, in the future, look at interchip communication as it relates to the data that's being forwarded to those? Because most likely it may not be UART. It could easily be, I've seen everything from SPI for certain devices to, I2C and things like that. So something to think about. Can we do that? Understand the functionality. Validating end-to-end security. What is the data flow? And is there obviously any flaws in the security? The one thing I'm looking for, and I expect I'll eventually see it, but maybe not on lock devices where they're actually letting the key flow all the way through the lock. But what about lock devices where a lot of the control is at the board level? It's designed to always work with a bridge. Won't necessarily work with not a bridge. Does the bridge do some of the processing and at that point fail to actually pass the key through, process it here and just tell the damn thing to turn on or off? And break that entire security from end to end. So I'm looking for stuff like that. Ejection attacks and fuzzing. Can we automate some of the fuzzing? So most of the fuzzing I did was manual. It was done for a very specific reason. 2 bytes here, 2 bytes here, 2 bytes here. Look for patterns. Am I able to alter anything? Can I still control the lock even though I change certain parts of the code? Those type of things, which are very revealing. Also, looking at it from both directions. I'm looking at attacking the end device. What happens if I can go back the other way? What if I can go back to the cloud? Because if I can identify the communication going back to the cloud, because it's telling the cloud the status of the device. Okay, so can I easily replay that data back out there and control it? As you've seen, there's no key mechanism for validation of the information going back. So at that point, there's a possibility that I can actually change and identify a different state of a device in the cloud that could impact the overall functionality or security of the device. Something to consider. Fault conditions, resets. Can I force the device into reset? Hey, if I send a key that's all Fs, what the hell happens? These devices have weird ways. Sometimes these devices have keys that are like fixed. As in, you can go up to the device and you can pin a number in. How does that play on the device when it comes to keying? Or in local mode, how do they compare? Can we go ahead and actually create a reset on the device that'll cause the device to fail into some state that it wasn't intended to go into? So let's go ahead and check that. Can I crash the device? Basically just freaking bricking it all together. And past research or testing I've done, I've been able to identify information on interchip communication that I was actually able to use to interact with the cloud services that led me the ability to identify all of the bridge devices around the world for a company and the ability to remotely reconfigure them to point to a device that didn't exist using data that I've gathered from this method here. Basically saying, hey, all these devices, point to the MAC address 000000, basically bricking the control of every one of the devices on the earth. So there's a lot of potential impact there around some of this stuff. And then again, data enumeration. What does the data mean? What can we construe from the data? How can we use that data? So thinking around those processes. Weaponizing technology. How can I take my bridge device and control your door lock is one of the goals. Could you do this with every potential device out there? No. A lot of them have good security, good keying mechanisms, rotating keys, unpredictable keys. But as key space gets smaller and smaller, and now that I have, as an example on this device, the ability to tell it to hook to any device, even though it was not configured to initially do that, it gives me the ability to inject into that device, particularly if I can figure out what the keying mechanism is. And if that's successful, or the key space gets small enough, it becomes brute forcible. So then we can basically program the whole thing up, take the bridge device, hook into it, use the built-in electronics designed by the company to target somebody and brute force control of the end-based IoT technology. That totally cool shit to me. So. Future, what are our plans? This is the big part. Like I said, this is part one. The next thing is I'm hoping by first quarter, I want to release a white paper around these methodologies, concepts, something we can all get value from. And of course, I want to point out, the reason why I did this as a phase one or part one, I'm looking for feedback from the community, thoughts around this process. Can you get value from it? What would you like to see? What's the end game? I don't want it just to be me. I want feedback from the community to help me make this move forward. Because the ultimate goal, as we mentioned up there, is tools. We want to produce tools. Kind of the best way to describe it. How would you like to have a burp proxy style capability on a UART communication channel? The ability to basically capture in the flow, halt it, let it go forward, or alter it, let it go forward. Also replay. Can I pull it over and do replay, alterations and replay? And the third one is intruder. Can we take like an intruder-like function, and now we can set it up, regex structure on it, and go, hey, start freaking fuzzing. So that's kind of where we're going at the tools. And of course I threw Metasploit out here. Metasploit has a hardware bridge that was developed by Craig Smith here about 1.5 years ago. We haven't really leveraged it in any cool scale. So I'm starting to think, you know, if we build this device, and what I'm thinking about doing from this whole concept, and just to point out the person who's going to help me do this is Matthew Kino, who is on the Metasploit team at Rapid7, has volunteered to help me with the coding process. I could do the coding, but it'd take me like 6 months to do something he could do in like 2 weeks. And I've done that a number of times in the past, and I started thinking, I want to move this project forward. I don't want to spend my nights writing shitty code. I'd rather have somebody that's really good at it, and Matthew's promised to step in and help me. So the goal is to release that code mid next year, because we want to get enough sample research done that when we go to write the code, that it will work in every example possible, or at least most of them. And of course, back to the Metasploit module, the ability to tie whatever we create into the hardware bridge. My train of concept on this tool is to be able to build it out like on a BeagleBone, and then we'll build custom shields to go on the top for interconnecting every one of the devices, possibly putting load capacitors on there so that we can get away from cutting the runs if that's possible. I still have to kind of work through some of the stuff on that. Like I said, I'm not an electrical engineer, but I will get it. It should be simple. Should be able to get it figured out. And basically we end up with a device with a shield on it, like some of those other devices, where you can easily just hook all the connections to it, and now you have full control to capture, fuzz, replay, all of these capabilities within the system. Of course, if we're going to capture, it's going to have to go through the device, so it's probably still going to have to cut the runs. That's kind of where we see this moving forward in the future. I hope everyone's interested in that idea and would find some value in it. I know a couple of my friends are very interested in getting involved in it. And in the end, when we release this, we'll kind of make it available. Obviously, we're going to open source the whole thing, not into keeping things quiet, because I want it to be used by other people so that we can actually make it better, and then also get feedback on it so we can add more functions and features. I don't know if there's another slide, but going forward, this is all UART communication, which is typically what's used for Bluetooth Low Energy. We want to be able to communicate and figure out all the communications that's used for Zigbee, Z-Wave, and all of the standard protocols that we're seeing, or the standard chips and communications we're seeing, to be able to get inter-chip communications available on all of those different protocols where it's possible. I mean, there may be some technical issues we may run into, but we'll work through those when we get there. So I expect this project to span out several years as we add more capability and more features to handle more inter-chip communication methods. And so here's my contact information. Don't hesitate to reach out to me. Follow me on Twitter. Shoot me an email. If you think I'm full of shit, shoot me an email. If you think this is brilliant, best thing since sliced bread, shoot me an email. The goal is to make this happen. Any questions at this point? Come on, you got to have some questions. Yes, sir. I mean, there's a lot of places. You know, when you go into a board, there's a lot of complexities, a lot of functionalities, and a lot of features in there. So in my opinion, there's always other places in there. Thank you. One of the things I ran into a while back, and it wasn't necessarily directly with this, but it was interesting how a device was actually being programmed by inter-chip communication. We had two processors, and one of them happened to be MRF49, which is a multi-frequency 915, 433, and whatever the 800 version of it is. And the company had put their protocol out saying what they were using and how it was configured, which was total bullshit. Because when I tried to do an SDR to capture this data, it's like none of this is working. Why? Inter-chip communication, which happened to be SPI, pulled down the data sheets, captured all that data, and there was 10 32-byte packets sent to the device. Compared that to the data sheet, it told us exactly how the MRF49 was configured to run, and then we were able to build the SDR to match it more appropriately, to interact with it. So there's always other places. This was kind of focused on end-to-end security. It's coming from here and it's ending up on this device over here, and this is setting in the middle. So very much focused on the data flowing through it. So if we're dealing with any other protocols or communication methods that it flows through to something, I think this plays a big role in understanding that end-to-end security. Well, yeah, that's interesting, but and there's a lot of good papers written on the subject out there, but there's a level of complexity dealing with, obviously, with RAM and the fact that it's parallel communication. And if you look at the board, they have all these like squiggly lines leading to RAM thing, because it's all very time dependent, so everything has to hit the chip at the same time. So to be able to tap into that, you can do it. I've hooked up and I've seen the data come through, but it's all in parallel, so then you got to put it all back together, and then all the proper timing sequence so you can put it back together. But there's some great papers out there. I've read a number of them. But yeah, let's not take anything off the board in the long haul when we're really trying to understand end-to-end security. And of course, with that there, I've had, you know, brainstorms where, hey, can I pull the RAM chip, put a device in there, piggyback that off of it, and be able to capture all the RAM communications, you know, as ideas. So I'm always looking at methods, how I can use this board to discern information, to really understand the overall security of a product. So that's definitely not off the board, maybe for this project here because of the complexity, but definitely not off the board as a project sometime in the future, which I'm always thinking about. So we're looking for a good name for it. And I don't want it to be some variation of burp either, let's be real. I just use that as a good example because people understand burp, the concept of burp. Most of what I found out on UART, based on how the device is designed, but most of the time I don't. Because I can come back and just play the same damn packet like 3 hours later and it freaking works. As you get into SPI, I2C, very much more time dependent, which could be more impactful that we'll have to consider. Any other questions? I thought there was one back here. Yes, sir. Okay, Craig Smith wrote if you know Craig Smith, he does transportation car hacking stuff. He wrote a module in Metasploit to give you the ability to connect to hardware used to test other hardware. And our idea is if we create this device as basically a piece of hardware using a BeagleBone, can we actually pair it to that and maybe automate some of the testing via Metasploit modules that we can create? That's kind of the concept. Yeah, you would take your machine, you would hook the BeagleBone up to it. It would set up a channel between Metasploit. It would set up a session, almost like a normal session, but then it could send command structures through there. Yep. Yes, sir. No, it was they had totally dropped the ball. There was no SSL pinning in that case. And yeah, which is common. And then they also had failures in API security. Yeah, well, basically what I did was I was able to identify vulnerabilities within the API, within the APIs originally, and then be able to take the replay data that I was playing with to alter that, because the APIs were failing on security, because they were expecting machine-to-machine communication, so there was a level of trust. They didn't think anyone would get between it.